In this section, we are learning about entropy and Gibbs free energy. We are ultimately interested in answering the question, will this happen? This being some reaction or process. So we want to know, we go to the lab and we mix X and Y. Are they going to react? Are they going to do anything? And the way we can answer that comes back to the concepts of entropy and Gibbs free energy. So we're going to be learning about those in the next couple lectures. So when we ask the question, will this happen? What we are actually asking in terms of chemistry is, will this be spontaneous? So we're going to start by learning about the concept of spontaneity. In chemistry, spontaneous means that a process or reaction will happen. It doesn't necessarily mean it happens fast. It could happen very slowly. It just means that it happens. In order to define whether or not a process would happen, we have to specify the temperature and pressure that we're looking at. So spontaneity, whether a process can happen, depends on what temperature and pressure it is at. We can think about some examples of spontaneous and non-spontaneous processes. An example of a spontaneous process would be a bike rolling downhill. A bike rolling downhill. We don't have to do anything to make our bike roll down the hill. It'll just go. A more chemical example would be if we specify we're at 1 atm and 25 degrees Celsius. The process of H2O solid, ice, going to H2O liquid is spontaneous, right? We know ice, if we put it on our counter, will melt. Likewise, non-spontaneous processes are those that just don't happen. For example, a bike will not roll uphill. Unfortunately. I actually live really close to the campus and I like riding my bike, and so every once in a while I'll ride it up to school. Well, not right now because we're not going anywhere right now, but I will sometimes ride my bike up to school, and I can tell you from experience it is quite unfortunate that bikes do not roll uphill, but they definitely don't. In terms of our chemistry example, we know that at 1 atm and 25 degrees Celsius, H2O liquid will not, become H2O solid, right? We can't put a glass of water on the counter and it will just freeze at standard temperature and pressure. And so you may have noticed that for both of these examples, whether we're talking about a bike rolling downhill, uphill, or water melting, freezing, the opposite of the spontaneous process was a non-spontaneous process. And that is going to be true for everything. So the reverse of a spontaneous process is a non-spontaneous process. And this concept is going to turn out to be relatively important a little bit later in this section. This is useful when we start thinking about reversible reactions, which we've been learning about when we learned about equilibrium. We learned reactions can go forwards or backwards. And so here we're again starting to think of reactions going both in the forward and the reverse direction. So in the forward direction, if it happens, it's spontaneous, and that reverse would then be non-spontaneous. We have established that processes can be spontaneous or non-spontaneous, but what makes it so? What makes a reaction spontaneous or not spontaneous? There are two ways we're going to answer this, But we can start about thinking what kind of features are more likely to lead to a spontaneous process. One of the things that is more likely to lead to a spontaneous process is an exothermic reaction. So the reason for that is that if we think about sort of an energy graph, and I'm not going to put numbers in here, but we're going to think about the energy of the reactants as being up here and the energy of the products as being down here. So if the reactants are higher in energy and the products are lower in energy, meaning that there is a negative delta E for the process, then the reaction is likely to be exothermic and likely to happen because it's releasing energy. And if this energy is released as heat, then it would have a negative delta H. It would be exothermic. And this is just a favorable process because we end up with a lower energy configuration. So it's favorable because we end up lower in energy. And that means a more stable configuration for matter. So one thing that can lead towards a spontaneous process is an exothermic reaction. But endothermic reactions can be spontaneous too. So that focus on the release of heat or the requirement of heat cannot be the only explanation for why a process is spontaneous or why it happens. Some examples of spontaneous endothermic processes include the evaporation of water, H2O liquid to H2O gas. The liquid is a lower energy, the gas is a higher energy. This is endothermic. It requires energy, it requires heat, but we know it happens, right? We know if we get out of the shower and we're all wet, that our bodies will dry on their own. We don't have to do anything to make it happen. So we know the evaporation of water is spontaneous, even though it requires energy, it requires heat. Another example of a spontaneous endothermic reaction is dissolving baking soda in water. And this is actually a reaction you could try at home if you want to, if you're looking for something kind of hands-on to do with chemistry. Get yourself a small Ziploc bag, put a couple scoops of baking soda in it, and then add a little bit of water to it, enough to dissolve it, so maybe like a 1/4 cup of water in a tablespoon or so of baking soda, maybe 2 tablespoons of baking soda, and squish it around and feel the outside of that bag. You're gonna see it feels cold. So dissolving baking soda in water requires heat. It's endothermic. And both of these instances, I'm assuming 1 atm, 25 degrees Celsius. So if there are processes that can be spontaneous, even though they require heat, there must be something else that explains what makes something spontaneous, what makes something happen. That something else is entropy. Entropy, which is abbreviated with a capital S, is a measure of how spread out a system's energy is in space. Oftentimes, entropy is described as chaos or disorder, which are situations that often have more entropy but are not the actual definition of entropy. So entropy is how spread out a system's energy is. The more disordered something is, the more spread out it ends up. So more disordered things have more entropy. There are a couple features of entropy that I want to highlight. First of all, entropy is not conserved. Entropy is not conserved. We've learned about the conservation of energy. We've learned about the conservation of mass or matter. These are things that can't be created or destroyed. Energy, or entropy rather, can be created. The entropy of the universe is constantly increasing. The entropy of the universe is increasing. So nature favors an increase in entropy. Even though entropy, this idea of a spread out system's energy, is a very abstract term, I think we can kind of think of it and think of practical everyday examples to understand how nature favors entropy. So, for example, I think about my kids a lot when I think about this topic. The other night, my toddler threw this absolute temper tantrum over something. I don't even remember what. And he went in his room and he dumped out 10 bins of toys all over the floor. It took him all of about 90 seconds to accomplish this. So toys everywhere. Half an hour later, my 11-year-old and I finished getting it all put back away. So the effort to make something ordered is substantial. The ease to make something disordered and spread out is minimal, right? It's easy to make a mess. It's hard to clean it up. You can think about laundry too, right? Like your clothes never come out of the dryer folded on their own. You have to input energy into that to make that happen. So nature on its own likes to leave things in these sort of disordered, spread out ways. And enforcing order takes energy and work. Entropy is measured in units of joules per mole Kelvin. So entropy is a temperature dependent property. Entropy values are always positive. The only thing that has an entropy value of 0 is a perfect crystalline substance at absolute 0. Nothing has a negative entropy value. Now, I'm talking about an S value specifically. This is going to change when I start talking about change in entropy, or delta S. So for S, absolute entropy, the values are always positive. And the values are relatively small, at least compared to enthalpy. Right, so enthalpy, delta H, we learned about a few months ago, and generally speaking, we can say enthalpy is heat. And so enthalpy, if we remember, the units of enthalpy are usually kilojoules per mole. So these are measured in joules because they're a lot smaller than enthalpy values, which are bigger and make more sense to measure in kilojoules. Standard entropy values can be looked up in the back of your textbook in Appendix 4, just like the enthalpy values were. When we look up the standard entropy, you'll notice that it has a degree symbol next to it, and that degree symbol just specifies that we are at standard conditions, which are 1 atm, 25 degrees Celsius. If it's a solution, it's 1 molar. We're going to see a little bit later in this lecture what we can use those standard entropy values for. First, I want to talk about some trends in entropy values. So in general, the trend for entropy is that if there's more motion, then there tends to be more space. And if there's more space, then there's more entropy. So if we look at a substance, and every substance can exist in 3 phases, solid, liquid, or gas, The solid with the least amount of motion is going to have the lowest entropy. The gas, which has way more motion and way more space, has way more entropy. So we can generally say that a solid has less entropy than a liquid, has less entropy than a gas. And this is assuming we're comparing the same substance. But even between substances, if we're comparing things that are solids or liquids to a gas, the gas will always win in terms of entropy regardless of the substance. Another trend in entropy is that a larger mass equals more entropy, and this is for monatomic species. So basically looking at atoms by themselves or a monatomic ion. The last trend is that the more complex a molecule is, the more entropy it has. And this would be for molecules of similar mass. So for molecules of similar mass, the more complex they are, the more entropy they are. Complexity for a molecule typically means more bonds. So the more bonds you have, the more atoms you have, the more entropy there is. As I mentioned above, we are sometimes interested in the change in entropy delta S. So we're looking at how the entropy changes throughout the process of a reaction, from reactants to products. There are a few reactions or processes that we can predict the entropy changes for. And we can't predict the numerical value, but we can predict the sign, whether they'll be positive or negative. So we can do this for phase changes. Anything that goes from a lower energy phase to a higher energy phase gains entropy. So melting, going from a solid to a liquid, we gain motion, we gain entropy. Vaporization, which is the same thing as evaporation. It's going from a liquid to a gas. Or sublimation, when we go, interesting spelling there, when we go directly from a solid to a gas. All of these increase motion and are positive delta S. Likewise, freezing, going from a liquid to a solid, we lose motion, so we lose entropy. So our change in entropy is negative. Condensation is the opposite of vaporization. This is when we go from a gas to a liquid. And the opposite of sublimation is deposition. And that's when we go from a gas to a solid. Another thing that will always lead to an increase in entropy is an increase in temperature. So this isn't necessarily a reaction or process, but whenever you increase the temperature of a substance, its motion increases and therefore its entropy increases. Opposite is true if we decrease the temperature. A decrease in temperature will lead to less motion and a negative change in entropy. The final feature has to do with gases. So a reaction that makes where the number of moles of gas increases. Increase in number of moles of gas. A reaction with an increase in the number of moles of gas. So the products have more moles of gas than the reactants. That's going to have a positive delta S. And the reverse, a reaction with a decrease in the number of moles of gas will lead to a decrease in entropy. So if you have fewer moles of gas product than you had of gas reactant, that would be a negative entropy. I'm going to recommend you pause the video and go to worksheet 17A and try number 1. See if you can predict the change in enthalpy of those. The answer key will be posted on Canvas for you to check your work. Although we can predict the sign of delta S for some processes, there are a lot of reactions and processes we cannot predict the change in delta S for, and so we need to calculate it. When we calculate it, we can determine both the sign, whether it'll be positive or negative, as well as the value. To do this, we're going to use those standard values from Appendix 4. The equation is the same one that it was for delta H. The delta S of a system, where the system is whatever your reaction or process is equal to the sum of the standard entropies of the products minus the sum of the standard entropies of the reactants. This N that I put in the equation stands for moles, and it comes from the coefficients of the balanced chemical equation. So it's our way of factoring in stoichiometry. You should pause the video here and try worksheet 17A number 2. Answer key is posted on Canvas for you to check your work. We can also calculate the sign and value for the change in entropy of the surroundings. So we learned when we learned about thermochemistry that you have your reaction and your process, and that's considered the system. And then everything else around it is the surroundings. So the change in entropy of the surroundings is entirely dependent on temperature changes. Entirely dependent on temperature change. And the temperature change of the surroundings is going to be dependent on the delta H of the system. So if your reaction is exothermic, it releases heat. That heat goes into the surroundings. The surrounding heats up. That means it has more motion, which means it has more entropy. If you have an endothermic reaction, that is going to cause the temperature of the surroundings to drop. It will have less energy and less motion, and therefore less entropy. So we can summarize here that for a positive delta H, which is endothermic, then we will have a negative delta S of the surroundings because it will be getting colder. And if we have a negative delta H in exothermic reaction, then we're going to have a positive delta S of the surroundings because it will be heating up and gaining entropy. The actual equation here for this is the delta S of the surroundings is equal to the negative delta H of the system over T. So this is sort of the second equation we need to know for this material. The first equation being the one from up above. In this equation, it's important to know that temperature should be in Kelvin. Must be in Kelvin because the units of delta S are joules per mole Kelvin. So we need it to be in Kelvin in order to get to the right units. And the other thing we have to note is that The delta H of the system is usually in kilojoules per mole. And so we should convert it to joules per mole before we plug it into this equation, which is simple. We just divide by, or multiply by 1,000 rather. So the negative sign takes into account this relationship here, that the positive delta H gives us a negative delta S, and the negative delta S gives us the positive, negative delta H gives us the positive delta S. So that's what this negative symbol here is for. At this point in time, I would recommend that you go to worksheet 17A and try number 3. You can check your work against the answer key posted on Canvas. We can also calculate the value of delta S for the universe. This is relatively simple because, well, it's simple if we've already done the above things. So if we have the delta S of the surroundings and the delta S of the system, then it's easy to calculate the delta S of the universe. So it just needs to be the combination of these two, the delta S of the system plus the delta S of the surroundings. Since we know that the delta S of the surroundings is equal to the negative delta H of the system over T, we can also write this equation as the delta S of the universe is equal to the delta S of the system minus the delta H of the system over T. The benefit of this version of the equation is that it puts everything in the perspective of the system. So it's a little bit easier to sort of think about everything from the perspective of the system. But either of these equations are fine to use. You can practice using this equation doing worksheet 17A number 3. So there were 2 parts to worksheet 17A number 3, and you should be able to answer both of them now. So why do we care about delta S of the universe? Why would we care about entropy beyond the entropy change of the system? Well, it turns out that this is part of the second law of thermodynamics, which tells us that in order for a process to be spontaneous, which means it happens, then the entropy change of the universe has to be positive. So again, nature tends towards increasing entropy. If the entropy of the universe increases, then that's favorable and is likely to happen, or does happen. If it would lead to a negative entropy change, then that would be unfavorable and would not happen. And since the opposite of what happens is a non-spontaneous process, then the opposite of a non-spontaneous process, something that doesn't happen, is a spontaneous process. That's a mouthful. Basically, I'm trying to explain why I'm saying in the forward direction here. A process that is non-spontaneous will be spontaneous in the backward direction. So the direction of the reaction is important to indicate here. It is kind of interesting to take this reaction from up above and think about it from a mathematical concept or a mathematical way that tells us a little bit about chemistry also. So we're going to have 4 different possible combinations here. We can have a positive delta S of the system and a negative delta H of the system. We can have a negative delta S and a positive delta H. Or we can have both of them be positive or both of them be negative. Regardless of what the value is for these first 2 situations, we're going to know what the sign is for delta S of the universe. So if delta S of the system is positive and delta H of the system is negative, we end up with a positive minus a negative. 2 negatives make a positive. So in that situation, delta S of the universe has to be positive, which means whenever you have a positive delta S of the universe and a negative delta H of the system, it will be spontaneous no matter what the temperature is. I'm going to move that positive sign over there so I have room to write. No matter the temperature. So at all temperatures, this is going to be spontaneous, even because we are gaining entropy and releasing heat. If the delta S of the system is negative and the delta H of the system is positive, we end up with a negative minus something, which only makes it more negative. So this has to be a negative delta S of the universe, and so it will be non-spontaneous no matter what the temperature. Okay, so this first one was spontaneous no matter what the temperature is, and the second one is non-spontaneous at all temperatures. For the last two cases, we're going to see we have a positive minus a positive. It could be positive, it could be negative. It's going to depend. So we can't predict for these last two cases. It's going to turn out that when both of these are positive, we have a process that's spontaneous at high temperature. And when both of them are negative, we're going to have a reaction that's spontaneous at low temperatures. So this might make sense to you, right? If something doesn't work in the lab, you might think, oh, maybe I need to heat it up to get it to react. It might make less sense for you to think, oh, it's not working, I need to cool it off. What would work when you cool it off? Well, think about making ice, for example, right? We can't make ice if we don't cool it down and put it in the freezer. So the process of water freezing requires low temperatures, whereas the process of water boiling requires high temperatures. I'm going to stop this lecture now, and we will pick up on page 4 with the next lecture. If you haven't already done so, go ahead and try those worksheet problems, and then also take the follow-up quiz on Canvas.